Vanakkam. Welcome to this course on biomedical instrumentation. In the previous video or in the previous set of videos, we looked at an introduction to EEG and EEG montages and why are montages important. In this video, we will look at the EEG system itself, the EEG machine itself, the amplifiers and sensitivity control, how much sensitivity you need for which amplifier this, and then filters, appropriate filters and digital analog signal processing, both are required, and then noise and writing part and paper drive, how to minimize noise. Note that EEG signals are about 1000 times weaker than ECG signals. ECG signals are of the order of millivolts, whereas EEG signals are in the order of microvolts. So, you need to have high gain and low noise. Remember, high gain does not always mean that it is better, always remember this. Okay. Having a high gain can reduce dynamic range, that is one. Sometimes if a single amplifier has a very high gain, then it might depending on the situation which configuration you use, sometimes your op amp might saturate. So, there are multiple challenges when it comes to having a high gain system and low noise. Noise must also be low, gain must also be high. When you amplify both the signal and the noise. Let us say that you are trying to wash a cloth that has a stain. You are because it has a stain, you are applying, you are adding a little bit more of the detergent. Now, that will definitely work on the stain, yes, but it will also work on those areas of the fabric that do not have stain. That is, it is likely to cause micro nano damage to the fabric. If you are saying, no, I am interested in keeping the fabric quality the same without actually affecting the, without actually damaging the fabric, but I want the stain alone gone, that is adaptive filtering. Then what you do, you have to do some extra effort. Then you identify those regions that have the stain and apply detergent only there, extra detergent only there, and then hand wash it a little bit and then put in the machine. But if you randomly put in the, if you arbitrarily add the cloth in the machine and then add a little bit more detergent, it is going to cause more damage to the entire fabric, entire cloth. Let us say that you are not interested in causing the damage, so you add less detergent, then the stain will not be gone. The classic signal to noise problem. In television ads or in web series, YouTube ads or whatever ads, they are saying hard on stains, soft on fabric. There is no such detergent. I think detergent companies are going to be unhappy with me. They say hard on the stains and soft on the fabric. Now, how is that possible? If you are hard on the stains, then you are hard on the fabric, right? Otherwise, how can you be hard on the stains? So, that's a fundamental, this is how marketing works, okay. This is how marketing works. But anyhow, that we have sufficiently digressed. The point is that I want to have a high gain and low noise. That means I should have a relatively very good idea of what noise means, what constitutes noise, so that I will not amplify that and I will amplify everything else. Sometimes it is possible for noise to have same characteristics as the signal. Now, that removing that is a big challenge. We will discuss that. We have discussed that previously. For example, movement artifacts. We have discussed that previously. We will discuss that again. You are interested in having high gain. What is high gain? On the order of greater than 1000, preferably 10,000 to 100,000, because your EEG signal is having amplitudes in the range of microvolts, and your reading systems usually read in the range of volts. So, micro to volts, you need 1 million or at least 1 lakh, minimum 10,000 gain you need, okay, low noise. So, common mode rejection essentially is the approach to eliminate interference from power lines and nearby devices, and this common mode rejection ratio minimum must be about 100 dB. Present day devices have about 110 to 120 dB, that is a lot of dB, okay. Remember dB is a logarithmic unit, it is not just in units, it is a logarithmic unit. And then passive filters, single stage passive filters that essentially control the frequency response, those that are high pass filters, low pass filters, notch filters. I already mentioned the frequency ranges of interest, above 0.1 hertz high pass filter, below 40-50 hertz low pass filter, we will discuss that again. And a calibration signal is usually used to verify and document the amplifier sensitivity. I am sending a calibration signal and check what the output is for that calibration signal. And it must do bedside amplification using a nearby box, connector box or electrode interface box that reduces signal loss, cable artifacts and crosstalk. It must also be able to measure electrode skin impedance. I already mentioned skin impedance must be below 5 kilo ohms for EEG to detect poor contact. Sometimes if you are using gel, after some time what you will have is loss of contact of the electrode. So, you may have to reapply gel over long periods. For example, if you are doing sleep study over a period of over the whole night, you are studying sleep study, you are performing a sleep study, then you are interested in measuring EEG over the whole night. During that time, it is possible that the electrode will dry out. Of course, modern day electrode systems have dry electrode configurations, but they come with their own baggage. We will discuss that. So, there will be electrodes, there will be input protection, and then there is an amplifier system. What is the gain? About minimum of about 10,000. Filtering, there are different filters, HPF, high pass filter, low pass filter and notch filter, and then ADC, at least 16-bit ADC, and then digital signal processing using a computer. The sensitivity that you see on the paper is essentially the gain of the amplifier times the writer sensitivity. Sensitivity is generally viewed equivalent to gain, but in this case what we are discussing is amplifier gain, and in this case we are discussing writer sensitivity. So, the total net sensitivity of the whole system is essentially the product of amplifier gain and writer sensitivity. EEG signals usually have from units of microvolts to hundreds of microvolts, require gains of 10 power 4 to 10 power 6 for accurate display. 10 power 4 means 10,000, 10 power 6 means 1 million. Just reminding ourselves, you know these things. Let us say if the writer sensitivity is 1 centimeter per volts, then the amplifier must have an overall gain of at least 20,000 for a signal of 50 millivolts. There are different types of gain control that I can have. A continuous gain control essentially equalizes sensitivity across all channels, different channels, all of them will have same gain. The other one is essentially the stepwise gain. This essentially increases sensitivity in fixed increments. Typically the gain is set so that 200 microvolt signal is able to be properly deflect the pen. Remember that artifacts, large signal artifacts can sometimes overcharge the coupling capacitors, thus distorting the output and causing instability. So, this is when would this happen? Moment artifact like this sometimes can cause major system instability. Modern EEG machines have some protective systems like deblocking circuits like in ECG to prevent these artifacts from overcharging the capacitors. Filtering is absolutely essential because blood flow can cause movement artifacts. Then any movement, as the person is speaking, eye blinking, all these things, facial movements, all these things will cause muscle artifacts or movement artifacts from the scalp and neck movements of this. It is not possible for the patient to remain completely stationary. A person is completely stationary when they are dead. So, there will be some movements, and these movements will cause slight displacements of the electrodes, causing motion artifacts. These artifacts are, depending on the situation, may be sharp high frequency spikes, sometimes may be having low frequencies. So, these kind of muscle artifacts, if it is a muscle artifact, then it may be removed by using low pass filters to remove them. The original signal is usually very noisy, distorted and filled with artifacts. You first do low pass filtering because the signal of interest is usually below 50 hertz, say 0 to 55 hertz, that will reduce artifact. Usually this low pass filter will be a 4th order Butterworth filter. Okay. This will essentially smoothen the signal. After the smoothing, you will have clean, relatively more interpretable EEG. I already have this cutoff frequency options. Low pass cutoff frequency options are 5.3, 1.6, 0.53 and 0.16. Filter ranges typically 15 hertz, 30 hertz, 70 hertz and 300 hertz. This upper cutoff frequency is adjustable for improved noise control. Notch filter at 50 hertz essentially removes the power line interference. You want to minimize the noise typically below less than or equal to 2 microvolts. I already mentioned 1 microvolt RMS is the acceptable noise. Remember, noise will span all frequencies. So, if you have higher bandwidth, that means that there will be more noise. So, if you are interested in a particular range of frequencies, it might be useful to limit the bandwidth to only the signals and frequencies of interest. These noise levels should be stated as peak to peak noise and not RMS to avoid misleading interpretation. Peak to peak, there is a difference. Most writing mechanisms, most of them use an ink type direct writing recorder to show the visual output. There is a paper driven by a synchronous motor, and it requires a relatively stable mechanism for accurate signal tracking, and there are selectable speeds, what speeds it will go, 15 mm per second, 30 mm per second, 60 mm per second, depending on the clinical need. Some assumptions that students make, I already mentioned one of them, is that high gain means always better quality, but then higher gain can sometimes affect dynamic range and can sometimes saturate that. That is a common, one of the common misconceptions that students have. Then digital systems do not require any sort of analog filtering. Essential part of this systems is an anti-aliasing analog filter. Analog implementation of the anti-aliasing filter is an absolute requirement for this. Even though you have digital signal processing capabilities, sometimes anti-aliasing filter, it is better to have an anti-aliasing filter in analog form. The other assumption is that if I have properly shielded cables, I can essentially remove all forms of interference. This is not true. Magnetic interference cannot be avoided by shielded cables. Some of the things to keep in mind. Remember, what is your goal? In this case, let us say my goal is to hear a whisper. Somebody is whispering. Let us say somebody is whispering, and in a stadium full of people, say 1 lakh people are there, 100,000 people are there, somebody is whispering. How do you, let us say I am interested in playing this whisper throughout the stadium. Now you want to make sure that you have an appropriately sensitive microphone to this whisper, and a noise cancelling technique to cancel all other noise, and then appropriate amplification and output system like amplifier followed by a loudspeaker, so that it can be transmitted throughout the stadium. Let us say I am interested in transmitting this, I am interested in broadcasting this whisper throughout the stadium, for example. Then you need to, it is a crowded stadium, people are always talking, right. So, in this case I am interested in having a sensitive amplifier with noise cancelling technique. So, I need to have a high sensitive, first of all proper sensitive microphone. I need to have a sensitive microphone and a high gain amplifier and noise cancelling technique. All of these are required for me. So, each neuron is essentially whispering. What you are hearing on the scalp is the activity of multiple neurons through volume conduction and through a whole bunch of, it is an ensemble activity. But one neuron is essentially only whispering. But I am interested in neuronal activity, or at least regional neuronal activity. That is my interest. I am interested in localizing regions. If there is no reason, if I cannot identify which activity is coming from which region, why even do EEG? That does not make sense. So, I need to find a way to localize this. But how? That is the question. So, it is a challenging process, it is a challenging topic. That is why people are still researching on this, right. It is an exciting topic and it is a challenging topic. Anyhow, with this we come to the end of this video. In this video, we looked at EEG machine amplifiers and sensitivity control and filters and signal processing. Remember, it is not all digital signal processing, anti-aliasing filters may need to be analog, and noise characteristics and writing part and paper drive. With this, we end this video. Thank you very much for your attention.